Okay, so today we're going to yet again continue chapter 3. I think this lecture and next lecture we'll finish up chapter 3. After that, we'll move into chapter 4 on induction, which is a very cool proof technique. You'll see that in 2 lectures or so. But today we'll talk about modular arithmetic. Okay, so this is still within chapter 3 somewhere. So I'll start today with a definition. Okay, so let a and b be integers. So let a, b, and z, and let n be a natural number. Okay, so as always in any definition, it's always very important, maybe in any mathematical sentence, to say exactly what your variables mean. We say that a is congruent to b modulo n. A is congruent to b modulo n. And we write the following: a congruent to b mod n, if and only if n divides a minus b. Okay, so I'm only making this definition for natural numbers n. And in fact, maybe I should even say here, greater than 1. Right, so we discussed at some point that the convention for natural numbers is, there's more than one convention. One convention is that 0 is a natural number. One convention is that the natural numbers start at 1. So here, let's just specify that I want n to be greater than 1. And I'm defining, so it's like I have a fixed natural number n, and it's like I'm defining what it means to say that a is congruent to b modulo n. This is how you should think about this definition. Okay, and what it means is that n divides a minus b. Okay, so some things to note here, right? Remember we defined this symbol, which is \mid last time. So this means that there exists an integer k such that a minus b equals n times k. That's what it means to say that n divides a minus b. Okay, also notice that here, like I should say that it's very nice to add parentheses here because you're saying that n divides this whole quantity. N divides this whole quantity. So it's good to set that quantity off in parentheses. And then I guess I should also tell you that this symbol in LaTeX is \equiv. And actually to get this, you should say \p mod n. So if you look up the problem set LaTeX files, you'll see that this is how I've typeset it. But as with any definition, the first thing we should think about is what are some examples? Okay, so let's just consider the following questions. True or false? I'll give you 5, which you should think about. Is 3 congruent to 19 modulo 4? Is 3 congruent to 19 modulo 3? Is 4 congruent to 1 modulo 3? Is 108 congruent to 4 modulo 4? And is 789 congruent to 6 modulo 9? Okay, so I want you to figure out whether these are true or false. So take a moment, pause the video. Okay, so what do these things mean? Again, we've just defined what the symbol means, right? So this will be true. 3 will be congruent to 19 modulo 4 if and only if 4 divides 3 minus 19. So does 4 divide 3 minus 19? Well, 3 minus 19 is negative 16, right? So does 4 divide negative 16? The answer is this is true since negative 16 equals 4 times negative 4. So because 3 minus 19 is a multiple of 4, we say that 3 is congruent to 19 modulo 4. Okay, we've already done 3 minus 19, so we know that 3 does not divide 3 minus 19 because that's negative 16. And so I would say that this is false. Or I could write 3 is not equivalent to 19 modulo 3. Right, so this says that this backslash or the slash through the 3 lines means 3 is not equivalent to 19 modulo 3. To get this, you just do backslash not backslash equiv. This is generally how you get a slash through any sort of symbol like this. Okay, on the other hand, it's true that 4 is congruent to 1 modulo 3 because 3 divides 4 minus 1. Okay, 3 divides 3. 4 is congruent to 1 modulo 3. Okay, it's also true that 108 is congruent to 4 modulo 4 because 4 divides 108 minus 4. Right, 4 divides 104. It's because 104 is 26 times 4. Okay, by the way, note that what I'm writing here in blue is clearly just scratch work. So if I were trying to explain this to somebody, if I were trying to write it up, I would of course need to include more words, say what I'm doing, but this is just some scratch calculations so that we can understand why these are true or false. And then this last one, so I need to know, does 9 divide 789 minus 6? So I'm just asking, does 9 divide 783? Which I guess it does, right? 783 equals 9 times 87. So this is true. Okay, so this is the definition of what it means. This is the definition of congruence modulo n. But the usual way that you should think about modular arithmetic, so you should definitely know the definition, but this is not necessarily the way that you'll always think about it. The way to think about it is like what I'll call clock arithmetic. So modular arithmetic equals clock arithmetic. Let's put this in quotes. So what do I mean by clock arithmetic, right? So if I say that right now it's 3 p.m. Okay, so look, and I ask you, what time is it going to be in 24 hours? You would say it's going to be 3 p.m. Right? So in some sense, what you're saying is that 3 plus 24 equals 3. Of course, that's obviously nonsense. 3 plus 24 is not equal to 3. 3 plus 24 is equal to 27. But the point is that every 12 hours, you like repeat the numbers. Right? So for example, if I said, if it's 3 p.m. right now and I ask what time is it going to be in 13 hours? Well, it's going to be 4, right? Because in 12 hours, it's going to be 3. So in 13 hours, it's going to be 4. So basically, every time you add 12 hours to the clock, the time that it is, it's like you added 0 hours. Right? Every time you add 12 hours, it's like adding 0 hours to the time. So let's say, so what times are sort of the same? So if it's 3 o'clock right now, in 12 hours, it'll be 15 o'clock. But 15 o'clock is just 3 o'clock. Right? In another 12 hours, it'll be like 27 o'clock. This is 24 hours after we started. But you know that this is also 3 o'clock. Right? So on a clock, right? If clocks were actually doing addition, so on a clock, these are all 3 o'clock, right? If it's 3 o'clock right now, we say this is 3 o'clock. In 12 hours, it's 15 o'clock. That's still 3 o'clock. So why are these all the same? These are all the same because they all differ by multiples of 12, right? So these two differ by 12, these two differ by 12, these two differ by 12, which means that these two differ by 36, which is a multiple of 12. So to say that these are all the same time on a clock is exactly to say that 12 divides 39 minus 3. It's a multiple of 12 after 3. So what I'm saying is that when you're looking at a clock, what you're doing is you're doing modular arithmetic modulo 12. So it's not true that 3 plus 24 is equal to 3, right? This is not true. What is true, though, is that 3 plus 24 is congruent to 3 modulo 12, because the difference of those two things is a multiple of 12. Right? So for example, if I asked you, like, oh, what time is it going to be 39 hours after 3? Well, in 36 hours, it's going to be 3 again. So then we're going to add 3 to that. It'll be 6 a.m., I guess. But if I don't care about the a.m. or the p.m., if I'm just looking at the clock, right, the clock is going to point to 6. How did I know that? Well, because in 36 hours, it's going to be the same time as it is now, and then I can just add another 3 to that. So the point is that on a clock face, you can do a bunch of arithmetic. I could say, oh, we'll add 39 hours to the current time. What time will it be? That's like, seems like it'll be some valid arithmetic. On the other hand, it makes no sense to say that 3 plus 39 equals 6, because 3 plus 39 does not equal 6. 3 plus 39 equals 42. But modulo 12, that thing is congruent to 6, which is sort of the answer that you want. Okay, so as you work more with modular arithmetic, I know this is, all I've done is I've introduced it, and maybe some of you know it from like your CS classes or previous math classes, but as you do modular arithmetic, basically the way that you think about it is, if you're working modulo n, it's like adding n is like adding 0. When you're on a clock, adding 12 is like adding 0. Okay, and so this modular arithmetic modulo 12 captures what happens on a clock face. Okay, so let me just say that this set here, I could write as, well, I could say this set here. Let's actually put them in a set. All these things are all of the integers a, such that a is congruent to 3 modulo 12. So all of these times will be 3 o'clock on a clock. Okay, like I said, this will become more clear the more you work with it, but you got to start somewhere. Okay, here's another question, which is, how is modular arithmetic related to evenness and oddness? Okay, and I want you to think about this for a second. See if you can try to understand evenness and oddness in terms of some kind of modular arithmetic. Okay, well, what are the evens, right? So the evens, right, are 0, 2, 4, 6, 8, 10, -2, -4, -6. And the odds, of course, are 1, 3, 5, 7, 9, -1, -3, -5. So what you notice, hopefully, is that the thing that seems to matter is that these things differ by 2 at every stage. So, right, these common differences are all 2. And so this suggests that maybe we should be working modulo 2 somehow. So, well, what is true is that since these things all differ by 2, all of these numbers are congruent to one another modulo 2, and all of these numbers, right, are congruent to each other modulo 2. So basically, to say that a number is even is to say that it's congruent to 0 modulo 2. Every even number appears on the first list. Those are just all the integers that are congruent to 0 modulo 2, or all the integers that are congruent to 2 modulo 2. To be odd means that you're congruent to 1 modulo 2. And basically, every single integer is either congruent to 0 or congruent to 1. So when you're working modulo 2, you have a bunch of integers that are congruent to one another. Those are the evens. And a whole bunch of integers that are congruent to one another. Those are the odds. And those cover all your possible integers. Which we'll see that some statements about evenness and oddness can be captured very well by this notion of modular arithmetic. For example, you've all known from a young age that if you add an even to an odd, you get an odd. Okay, so you could prove that directly. You're capable of it for sure. But another slick way to do it is to state it in terms of modular arithmetic. So let me state a theorem, which I will not prove. I will discuss, however, which you will prove on the problem set. So to prove on a problem set. Here's the theorem. Okay, so let n be in n. I guess I should say n greater than 1 here, just to be totally unambiguous. Let me add it to the notes while I am not going to forget. So just give me 1 second here. Okay, then the relation blank is congruent to blank modulo n is reflexive, symmetric, and transitive. What does that mean? Okay, so that is, so 3 things. It's reflexive, it's symmetric, it's transitive. And hopefully, if you go all the way back to the properties, the axioms from the first lecture on chapter 3, you'll remember that these 3 properties were things that we assumed about equality: reflexivity, symmetry, and transitivity. So we should know what these mean. Reflexive means, so to say that equality was reflexive said that every number equaled itself. To say that equality was symmetric said that if A equals B, then B equals A. To say that equality was transitive was to say that if A equals B and B equals C, then A equals C. What this theorem that you're going to prove says is that, oh, also congruence modulo n has these same properties. So for all integers a is congruent to a modulo n. This is what reflexivity should mean. So actually, you should try to fill these in before I fill them in. So maybe pause the video and fill in the rest of these. Okay, so what is symmetry? It says for every integer, pair of integers a and b, if a is congruent to b modulo n, then b is congruent to a modulo n. And what is transitivity? For all triples of integers a, b, and c, if a is congruent to b modulo n, and b is congruent to c modulo n, then a is congruent to c modulo n. So this is what we mean if I say that the relation congruence modulo n is reflexive, symmetric, and transitive. Okay, but what is this really saying? This is really saying that this thing that we introduced, congruence modulo n, behaves a lot like equality. So this is the upshot. This is saying that this relationship, congruence modulo n, behaves a lot like equality, which hopefully is not that surprising if you think about clocks. Again, 3 plus 12 or 3 plus 24 is not equal to 3. It's not equal to 3 because it's 3 plus 24 is 27. That's not the same thing as 3. However, hopefully it's not a surprise that on a clock, 3 plus 24 is basically equal to 3. Right? Like that basically kind of makes sense because the relationship between 3 plus 24 and 3 is basically like the relationship of equality. Right? Also, like if 3 o'clock equals 27 o'clock, then 27 o'clock equals 3 o'clock because basically it behaves like equality. Right? And then if it's 3 and it's 27 and then you add another 24, so 27 should be the same thing as 51. It shouldn't be any surprise that 3 is the same thing as 51 because basically all those things are all basically like 3 o'clock on a clock. So all this says is that this congruence modulo n notion that we defined behaves much like equality, even though it's not equality. So maybe I should say that. Even though it is not equality. It does satisfy these 3 properties and more properties that we'll see in the next lecture. Okay, so we will continue learning more about modular arithmetic. But let me circle back to evenness and oddness, which we saw is actually, you can phrase it in terms of modular arithmetic too. So it's, I mean, it's all sort of the same topic because the nice thing about evenness and oddness is that you're very familiar with it, but it captures a lot of the ideas behind modular arithmetic. So if we study evenness and oddness first, it's a more comfortable place to start. Then we'll prove things in general about modular arithmetic, right? Like things that are true modulo 2. A lot of those statements will be true modulo n if you just alter them appropriately. Okay, also, I still owe you the theorem that every integer is even or odd, but not both. So that's what we'll try to, by the end of today's lecture, we'll try to prove that. Okay, so here's a first lemma. So maybe no one has told you what a lemma means. So I guess that's my first job as your professor. So a lemma is a result that is used to prove another result. Okay, so to be honest, in mathematics, like a lemma, a proposition, and a theorem all sort of mean the same thing, which is a mathematical result that is proven to be true. The difference between them is really just one of connotation. So like a theorem is like the big main goal that you're after generally. So if you read like a math paper, like the main things that the authors are trying to prove are called theorems. Now, along the way, you sometimes need to build up some other things that you know are true first that you want to use in proving your big result. So if you've proven something that wasn't really what you're trying to prove, you just need to use it later, you might call it a lemma. So a lemma is a result used to prove another result. And like a proposition is generally like somewhere in between a lemma and a theorem. So you're not just proving it to prove another result, but it's maybe not like the main point. It's like, oh, this is an interesting result on its own, but it's not the main thing that I'm aiming for. So these have some sort of a hierarchy of like importance. But to be honest, actually, I think it's better to have a lemma named after yourself, because if a lemma gets a name, it means that it's useful for proving lots of different results. So like, I don't know, like Gauss's lemma. Probably if you Google famous lemmas, you'll get like a bunch, right? There's like Euclid's lemma. There's like Burnside's lemma. This is really famous. So like there's of course things like Gauss's theorem, right, which is maybe sounds fancier, but to be honest, I think it's more pleasing to have a lemma named after you than a theorem. But I'm just totally digressing here. Someone ought to tell you what a lemma is, so I just did. So now you know. Maybe another thing that you should know is that the plural of lemma, you can say lemmas. In fact, if you want to seem like a normal human being, you should probably say lemmas. But you can also pluralize lemma by lemmata. But you shouldn't, because it'll make you seem extremely pedantic, which is, as we sort of discussed in this class, sort of my thing, kind of. But I remember in grad school, one of my office mates was writing some sentence in a paper or his thesis or something, and he had proved like 3 lemmas or something in order to prove another theorem, and he was saying, should I say by the previous 3 lemmata? And then we all made fun of him. You can make fun of your friends, right? It turns out that also you can pluralize dilemma, right? Like you hopefully are all familiar with the word dilemma, like a difficult decision, can actually be pluralized dilemmata too, but very few people do it. But I guess you could. Okay. Oh, I haven't stated the lemma yet, right? All I've done is I've told you about what the word lemma means and how it's pluralized. What's the lemma? Let's state it for good. Let n be an integer. Then n is even if and only if negative n is even, and n is odd if and only if negative n is odd. Okay, so the proof here for even and odd are actually quite similar. So because I'm your professor, I don't have to prove everything in class. I can let you prove some things. So let's just prove the even case, and I will let you prove the odd case, which you should do. It's not difficult. It's pretty much the same thing as the even proof, but you should just try to write it up carefully in your notes. Okay, so I'll just prove the first assertion, which is n is even if and only if negative n is even. So let's prove this. If n is even, what does that mean? By definition, there exists an integer k such that n is equal to 2 times k. But then negative n equals negative 2k. So why is that even? Because it's 2 times something. It's 2 times negative k. And we know that negative k is also an integer if k is an integer. right? And negative k is in z, so n is even. Sorry, negative n is even. Right, similarly, or maybe I should say conversely, right, because I'm proving the converse of the if and only if. If negative n is even, then there exists an integer j such that negative n is equal to 2 times j. Then n equals negative 2j equals 2 times negative j, so n is even. Okay, so the odd case you need to just write out. You actually need to do a little bit of work because to turn a -1 into a +1, but I trust that you should be able to do this. So I ask you to complete the proof. So odd case is left as an exercise. Again, it's not difficult. Also, the result, this lemma is not at all surprising to you, hopefully. So it's just an issue of, can you write it up very nicely and cleanly, which I want you to get practice doing. Okay, so how am I going to use this lemma? I'm going to use this lemma to prove the following theorem, which is let n be an integer. Then n is even if and only if n minus 1 is odd. Okay, so this is almost getting at every integer is even or odd, but not both, which will be the next result that we'll prove. This is what we're trying to prove. But for now, what we're going to prove is n is even if and only if n minus 1 is odd. Okay, so this is a biconditional, so I'll just tell the reader we will prove both directions separately, so they know what I'm doing, since it's going to be a little bit involved. And I'll give my reader a signpost that says that I'll prove the forward direction first. I'll prove that if n is even, then n minus 1 is odd. Okay, so suppose n is even. What does that mean? By definition, there exists an integer k such that n is equal to 2 times k. Okay, now what am I interested in? I'm interested in n minus 1. I'm trying to show that n minus 1 is odd. So what I can do is I can subtract 1 from both sides by using theorem 38, which is that we can add or subtract the same number to both sides and maintain equality. So by theorem 38, therefore, n minus 1 equals 2k minus 1. Okay, well, I need to show that n minus 1 is odd, which means I need to show that it's 2 times something plus 1. Right now I've shown that it's 2 times something minus 1. So it's not quite what I want. What I want is 2 times k minus 1 plus 1. So if you do this arithmetic, right, maybe it would be better to help my reader to do this. 2k minus 2 plus 1. That's the same thing as 2k minus 1, which is 2 times k minus 1 plus 1. Now it's 2 times something plus 1, and this something is an integer by closure of the integers. So by closure of the integers, k minus 1 is an integer because k is an integer and 1 is an integer. So n minus 1 is odd by definition. It's 2 times an integer plus 1. Okay. The reverse direction is suppose n minus 1 is odd. Then there exists an integer k such that n minus 1 equals 2k plus 1. Maybe if I mean, this would be okay, but maybe to be very clear, I use a different letter here. Okay, then n, which is n minus 1 plus 1, is the same thing as 2j plus 1 plus 1, which is 2j plus 2, which is 2 times j plus 1. Right? So this string of equalities is okay in a sentence as long as it's in the midst of a sentence. Right? And now, again, by closure of the integers, j plus 1 is also an integer because j is an integer and 1 is an integer. So n is even by definition. Okay. Now, I've proven that n is even if and only if n minus 1 is odd. I am ready to prove the main theorem after, which is that every integer is even or odd, but not both. Okay, so let me first discuss the strategy of how we're going to prove this. So next theorem, which will be on the next slide, is every integer is even or odd, but not both. Okay, so what I want to use is I want to use some theorems that we proved last time, which in your notes, I can just pull them up, right? Where is it? The integer 1 is odd, and the integer 1 is not even. I want to use these two results. So I know that 1 is odd. I also know that 1 is not even. But now, by this theorem that we just proved, since 1 is odd, I know that 1 plus 1 is even. Right? 2 is even if and only if 1 is odd. So I know that 2 is even. And since also I know that 1 is not even. So by this biconditional, since 1 is not even, it means that 1 minus 1 is not odd. So I know that 0 is not odd. So basically, from the fact that 1 is odd but not even, I can get that 0 and 2 are going to be even but not odd. Right? Because I guess you could also prove that if n minus 1 is odd, then n plus 1 is odd. You could also prove that if n is even, then n plus 2 is even. So then I'll know that 0 and 2 are even but not odd, and then I can sort of use this result again to get that -1 and 3 are odd but not even. And I keep on going. -2 and 4 are even but not odd. So I can sort of start from 1, which I know something about, and then this theorem allows me to move out one at a time and sort of know that the thing should alternate between even and odd. Okay, now the best way to do this is rigorously, I think, the best proof technique is something called induction, which, as I mentioned, we'll cover in chapter 4. So here I'll give you an alternate proof. So you could prove this by induction. Maybe we will when we get to that point. Here I'll provide an alternate proof because we can prove this using the technique of infinite descent, which is a technique that we discussed last time. So at some point last time, right at the beginning of last time, we talked about infinite descent, proving that something doesn't exist in a well-ordered set. So there's a way to piece together a proof using infinite descent, which I think is not as good as an induction proof. But we haven't learned induction yet, right? So I'll take what I can get. So here's a theorem. Every integer is even or odd, but not both. Okay, so for the proof, the first thing I'll do is I'll just prove it for the positive integers. Okay, but if I prove it for the positive integers, then I can use this lemma, which relates the evenness or oddness of n to the evenness or oddness of negative n, to get it for all the negative integers as well. And then also you can prove by hand that 0 is even, but it's not odd. I guess we can already prove that because we know that 1 is odd but not even. So this is sort of a piecemeal proof. So I'll just say first we will prove the statement for the positive integers. Using infinite descent. Okay, so suppose for contradiction, so I'm trying to prove that something doesn't exist. So let's suppose that I have a positive integer n, such that either 1, n is both odd and even, or 2, n is neither odd nor even. I'm trying to prove that this n doesn't exist, right? I'm trying to prove that every positive integer is even or odd, but not both. So let's suppose that I have something that's either both or neither. Let's try to prove that this doesn't exist. Well, since if I look at the whole set of these, that's a set of positive integers, it will have a least element. So by the well-ordering property of the positive integers, or of sets of positive integers, let's let n be the smallest such positive integer. Right? If an integer exists like this, there's going to be a smallest one. Okay, now of course there's two cases. Okay, one, so if n is both odd and even, then by the theorem we just proved, n minus 1 is also both odd and even. Let's say both even and odd. The point is that if n minus 1 is odd, sorry, if n is odd, then n minus 1 will be even. If n is even, then n minus 1 will be odd. Okay, well, n was supposed to be the smallest positive integer that was both odd and even, or neither odd nor even. Which means that n minus 1 can't be a positive integer. Right? So since n minus 1 is smaller than n, and n was the smallest positive integer with this property, therefore n minus 1 cannot be a positive integer. But this means that n was positive and n minus 1 was not positive, and 1 is the smallest positive integer. So this implies that n minus 1 equals 0, so n equals 1. But we know that 1 is odd and not even, which is a contradiction. But 1 is not even. We proved that, which is a contradiction. Okay, case 2, if n is neither odd nor even, then by the previous theorem, n minus 1 is also neither even nor odd. Because if n is not odd, then n minus 1 is not even. And if n is not even, then n minus 1 is not odd. So again, by the same argument as before, as in case 1, this means that n is a positive integer, but n minus 1 is not a positive integer. So this means that n minus 1 is 0 and n equals 1, but n is odd, which is a contradiction. So at least for the positive integer case, we know that every integer is even or odd, but not both. And now we can use the lemma from before, right? Hence, we have established the result for positive integers. Now, every negative integer can be written as negative n for some positive integer n. Because that's the definition of being negative. It means that your additive inverse is positive. So by the earlier lemma, right, we know that every positive integer is even or odd, which means that n is even or odd, but not both. But the previous lemma says that negative n is even if and only if n is even, and is odd if and only if n is negative n is odd. So by the earlier lemma, negative n is even or odd, but not both. And then I guess we haven't done 0, but 0 finally. 0 is even, since 0 is equal to 2 times 0. And 0 is not odd, since if so, 0 minus 1 equals negative 1 would be, oh, sorry. If 0 were odd, then by this theorem, 0 plus 1 would be even, right? So since if, let's say like this, 0 equals 1 minus 1 were odd, then by the previous theorem, 1 would be even, which it is not. Right? If n minus 1 is odd, then n is even. Therefore, we've proved this result for the positive integers, the negative integers, and for 0, which means that every integer is even or odd, but not both. A little bit of work, a little bit of work. All right, so I'm tired. I think I'll leave that there for today. Next time we will continue talking about modular arithmetic, and we'll learn an extremely classical proof about rational and irrational numbers. And then after that, the next lecture, we'll start talking about mathematical induction. So lots of fun stuff coming up, I promise. So I'll leave it here for today.